Friends, let's draw shear force and bending moment diagram for the given beam shown in the figure. So we have got a cantilever beam having A as a free end and B is a fixed end. So there is a uniformly distributed load of intensity 3 kN per meter acting on the beam from point C to point B. There is also a point load of 2 kN acting at free end of the cantilever beam, that is point A. Distance between point A and C, this much length from point A to C is 0.5 meter, while this much length from point C to B is 1.5 meter. So the overall span of the beam is 2 meters. Now we have to draw shear force and bending moment diagram for this particular beam. Okay, so let's see how we can proceed further to find shear force and bending moment diagram. So here we will start with the solution. Our first step is to draw free body diagram of this system. So if you look at here, this is the free body diagram. In the process of drawing free body diagram, we remove all the supports, and at that point of support we represent the forces acting on the beam. Since this is a cantilever beam, friends, at point B we will get a support reaction RB. Okay, it will be acting upward direction because all loads are acting in downward direction. To balance this load, there has to be an upward reaction acting at point B, that is RB. And since this beam has tendency to rotate in the anti-clockwise direction like this, okay, so to prevent this rotation there will be a reaction moment acting at point B that you can call as MB, and this reaction moment will be in the clockwise sense in order to prevent the anti-clockwise rotation of the beam. So there is a clockwise reaction moment acting at point B, that is we are calling as MB. So that I have shown here, the reaction force RB acting in the upward direction at point B, and there is a reaction moment of clockwise sense acting at point B. So always remember, the fixed end of a cantilever beam will have support moment reaction as well as support force reaction. This is very important point to remember. So this is basically we have drawn the free body diagram. So our first step is to draw a free body diagram, and from this free body diagram we shall find all the support reactions and support moment reactions. Okay, so step 1 is to calculate support reaction, that is RB, and support moment reaction, that is MB. So step 1 is to find reaction force, that is RB, and reaction moment, that is MB. So friend, we know the condition of equilibrium, that is summation of forces in the vertical direction 0. So sum of all vertical forces acting on the beam will be equal to 0. Similarly, summation of all horizontal forces, I am calling horizontal as Fx, that is x direction, will be 0, and summation of moment of forces, you can take any point, about any point, will have to be 0. So these three conditions are called as condition of equilibrium. Now as we know that there is no horizontal force acting on it, so this particular condition will be ruled out. So only we have summation of vertical forces equal to 0 and summation of moment of forces about any point will be 0. So let's take this particular condition and proceed by summation of all the forces in the vertical direction will be 0. So this will give you a very simple outcome. I am going to take upward positive and downward negative. This is a downward force 2 kN, and this is also downward, but this is the force intensity. We have to convert this force intensity into a point load in order to calculate the forces. Okay, so what I will do is I will convert this into point load. So it is 3 kN acting on 1 meter. The length is 1.5, so it is going to be 3 kN into 1.5. So if I do this value, it is going to be 4.5 kN. So this is intensity which is given in terms of kilonewton per meter, while this will be in terms of kilonewton because I have multiplied with the length, that is 1.5 meter over which it is acting. So now this is the point load equivalent of this particular load intensity acting on this particular length. Okay, now where it is going to act is an important point. It will always act at the midpoint of the length of the uniformly distributed load. So 4.5 kilonewton is going to act at the center somewhere here, we can say. So I'll draw it here somewhere. So maybe it will be acting somewhere here, we can say. So this is the location of all this uniform distributed load converted into a single point load. This is going to be 4.5. okay, that's a very important point to remember. Now I'll be using this point load for my calculation. So let's do it, friends. So friends, I am going to use the first condition, summation of forces in vertical direction equal to 0. So remember, y indicates the vertical forces. I am going to follow a simple sign convention that all the upward forces are positive while all the downward forces are negative. So upward force is RB, so I will say positive RB, and then this 2 kilonewton is acting downward, so minus 2 kilonewtons, I have converted this uniformly distributed load into a point load 4.5 kilonewton. So that is also acting downwards. So I'll be using this one. So minus 4.5 kilonewton, friends, and that is going to be equal to 0. So I shall bring this and this term towards right. So I'll be getting RB equals 2 and 4.5, that is 6.5 kilonewton. It's very simple to understand that all the upward forces must be equal to all the downward forces. So RB equal to 2 plus 4.5, that is 6.5 kilonewton. Straightforward. Now we have to also find out the moment reaction MB. So for that I'll be using second condition, the summation of all the moments of forces at any point equal to 0. You can take any point, friends, but I'll be taking point A. So by using condition, summation of moment of forces about point A, let me take. So for that I'm going to hold my point, this point, and like a hinge will apply all these forces and see how it is going to rotate. So this 2 kilonewton is acting same point, so it will not cause any moment because its distance from point A is 0. Now second force is I'm going to use this point load, which is the equivalent of this uniformly distributed load. So 4.5, and the distance, if you see, it will be center point, so it is 1.5. so it will be acting somewhere at the center here. This distance will be 1.5 divided by 2, that is 0.75 meters. So now we'll find out the moment of this 4.5 kilonewton about this particular point. So the distance of this particular force from this point is 0.5 plus 7.5, so it is going to be 1.25 meters. So 4.5 is the force and this distance from here is 1.25. So we'll get, therefore, now this is going to rotate the beam in the clockwise direction like this. Okay, so clockwise I'm going to take positive sign convention. You can even take vice versa also, no issue, but for here I'm considering clockwise. There is no restriction on sign convention. So you can say it is going to be clockwise. So clockwise taken as positive due to this force. So it is 4.5, it is plus 4.5 times 1.25. So this is, we got the clockwise. Now another force acting is this RB, and the RB is acting such that the beam about this beam is going to rotate in the anti-clockwise direction. Okay, like this. So RB into this distance, that is 2 meters, is going to be positive because it is rotating the beam in the anti-clockwise direction. So we got minus RB into 2, that is moment of this force. And if you look at here, there is a moment acting at this particular point, which is a clockwise moment. Okay, so this clockwise moment will create clockwise rotation about this point. Okay, this point is fixed here, so we have kept this point free. So you will see, if you apply this kind of moment, your beam is going to tilt or rotate something like this. Okay, because this point is free. Getting or not? So this moment, which is actually clockwise moment over here, but this point is free and this point is fixed, has caused this kind of rotation, that is clockwise rotation. So any moment, if you apply any point, will have some effect on this particular point, which is hinged. I have kept this point hinged for calculation of the bending moment caused by various forces. Okay, so now this additional bending moment would come. So we will be getting like this, friends, plus, because it is clockwise, MB, and that equals to 0. Please remember, this is very interesting point here. This was clockwise, hence it is positive. This is anti-clockwise, hence it is negative, and this is again clockwise, so it is positive. Like that we got. Okay, now we will have to solve this equation in order to find MB. So we'll bring all these terms towards right hand side. This RB value is 6.5, so I'll put that value. So 6.5 into 2, and this will become negative, so minus 4.5 into 125. So now if you simplify this, 6.5 into 2 is 13, and this is 5.625. So further simplification will give you the moment reaction acting at point will be equal to 13 minus 5.625, that is 7.375 kilonewton. So we got value of moment reaction acting at point B. So this was step 1, where we draw the free body diagram and we calculate the force reaction and moment reaction. So friends, now let's talk about the next step. This is called as step 2. So in step 2, we calculate the shear forces at various points to find shear forces at various points of beam. So as we have already understood, I have already explained in the previous videos, we have to move from one end of the beam to towards the another end. So we'll be considering a plane like this and we'll be moving towards So what we can do is we can start from here. Generally when we do cantilever beam, it is better to start from the free end. So whenever you are doing a cantilever beam, it is better to start from free end, because if you start from free end, the procedure becomes quite simple. So let me show you how. So I'm going to start from here, let's say. So I'm going to consider section just before point A. So when you start from this particular section, when you keep your section here, we have to look at the left hand side of this particular section, and we have to see how many forces are acting over here. So if you see the left hand side of this particular section, there is no force acting. Okay, so there is no force acting over here. Therefore the shear force at point A, just before point A, is going to be 0. So I'm going to write shear force at point A, just before point A. So I'll call just left. J stands for just and L stands for left. Just left of point A, and then there will be next calculation just right of point A. So like that we will be moving our plane from just left to just right. So when I am just left of this particular plane, there is no force this plane has covered. You have to look at the left hand side of this. So no force has covered this. So it means it is going to be 0. I am going to cross this particular plane just right of this particular point A, somewhere here. Okay. So once you cross it, you will see that this force would come into the picture. This force is going to come into the picture. Okay. There was no other force over here. Now we have just right a force of 2 kilonewton. Now if you look at here, this is acting downward, so we have to follow sign convention. So let's do that. Sign convention for shear force, because we are doing shear force calculation, so it is sign convention of shear force. If you have plane like this, so if shear force is acting upward direction in the left side of this particular sectional plane, then it is taken as positive. So this is taken as positive, and if it is acting downward side, the right hand side of this plane, then also is taken as positive. Please understand, left hand side upward is positive, right hand side downward is positive. So these are called as positive shear forces. Positive shear forces. So we'll see the next case here. We have this plane or sectional plane we have, and if your force is acting downward, okay, when it is acting in the left hand side of this particular plane, or it is acting upward when it is acting in the right hand side of this particular plane, these two cases are taken as negative. They are negative shear forces. Okay, so please remember, this is a very important point here, the sign convention. Okay, so now if you look at here, we are considering only the left hand side forces of this particular sectional plane, because we are going to move from left to right. Okay, always we'll be seeing the left hand side forces like that. So left hand side upward is positive and the left hand side downward is negative. So this I am going to follow. So here if you look at, this is acting in the downward direction and it is left hand side of this particular plane. So this is going to be negative. So minus 2 kilonewtons. Hopefully it is understood. Now I'll move the plane from here to here, just before point C. But if you see, if I just cross the point C also, there is no much of force included. It is same force as it is. Okay. Whenever uniformly distributed load start, there is no use of going left and right, because there is no much force gets included just by crossing this particular point. Okay, so instead of writing left or right, in such kind of situation we should only stick to the point C. So we'll directly write down shear force at point C. That will be better option. So I'll be writing shear force at point C. Let's do it, friends. So shear force at point C. So if I put my plane just at point C, so what a force is there in the left hand side? Only this force is coming. Okay, there is no other force has come to the picture, so I'll write only this force, that is going to be minus 2 kilonewtons. Okay, suppose in a case we got a point load at this particular end, so moving from left to right would have given some variation, but here though there won't be any much variation, because just left and just right a very small distance, so there is very small amount of force would come that we cannot find also, right? That is why point C, we always take the starting point if it is UDL, provided no point load is acting at the corner of it. So now we are here. So as I am going to move this plane from C to further, you will see that more and more forces will be included. Okay, for me it will be difficult to take number of points like that. Okay, but I want variation of forces like this. So it means instead of going like this, so we shall do one very small calculation And that is what we take a plane somewhere at arbitrary distance. Let's say I am considering my plane here somewhere. So I am calling this plane as XX plane. From here to here I am going to consider this distance as x, small x. So now I'll be finding the shear force at this particular arbitrary location, which is distance x from this point C to this particular plane. So that I'm going to call as shear force at plane XX. And that is I'm writing as SFX. Okay, this is very interesting to know. So now if I want to find shear force over here, so this force would be coming into the picture, and this much uniformly distributed load also would come into the picture, and both of them are acting in the downward direction, right? This is also negative and this also be negative, but I have to calculate this much, the value of this shear force. So distance is x, so I have to multiply this load intensity 3 kilonewton by distance which is x from here to here, so it is going to be 3 into x. Okay, so let me write down, this is downward minus 2, and then this is 3 into x, again minus. So like that I'll be getting the shear force in terms of variable x. So as I'm going to change the value of x, my shear force will be changing. So now what we shall do is we will take this equation and we will try to put the different values of x from point C to B so as to get distribution of shear forces from C to B. So we have point, let's say here, so I'm starting from point C. So at point C x is going to be 0, friends, because we are starting from here. So your plane would come here, x equal to 0. Now in between this, let me take few points. So let me take one point somewhere here, let me call this point as D, and one point somewhere here, let me call point E. So here x is going to be 0.5 and here x is going to be 1, and here B is already x equal to 1.5. So like this 3 point I have put just for simplicity. So A, B, C, D, let me say this point is D, here x equal to 0.5. Next we have E where we have x equal to 1, and last point B where x is going to be 1.5. So hopefully this is clear to you. All are in the meters. Okay, so this is the point B. Okay, so we got all these points. The shear forces at the corresponding point, okay, is given by minus 2 minus 3x. So let's calculate. So I'm going to put first x equal to 0 because at C x is going to be 0, friends. We are starting from here. So you'll be getting shear force at point C would be only minus 2 kilonewton. We have already calculated that, minus 2 kilonewton. Now we'll have shear force at point D. So x is going to be 0.5. So minus 2 into minus 3 into 0.5. So this is going to be, friends, minus 2 minus 1.5, so minus 3.5. Okay, this is very simple. So now we have to find shear force at point E where value of x is 1. So shear force at point E is going to be minus 2 minus 3 into 1 is going to be minus 5 kilonewtons. And last, at this particular point where we have B, the shear force at point B is going to be minus 2 minus 3 into, here value of x is 1.5. So 3.5 into 1.5 is going to be 4.5, minus 4.5 and minus 2 is going to be minus 6.5 kilonewton. Okay, so we got the variation of shear forces from point C to point D, and remember, since shear force is a function of single degree variable x, right, it means it is a linear variation. This is a very important point to remember. This variation is called a linear variation. So linear variation will give you linear curve, that is straight line. Okay, so linear curve, that means straight line. So from point C to B, the variation of shear force appears like a straight line. Okay, it will be a straight line variation. Please remember, shear force variation will be straight line from point C to point B. We will see later on when we will plot the graph. So we have reached at point B, friends, but now we have to cross the point B and we have to go to just right of the point B over here. Till B, we have not included this particular force, that is RB. Okay, but as we cross the point B, we will be getting this particular force also in the picture. So that I will write down here, that last and very important point, that is shear force just right of point B. okay, because wherever there is a point load, we have to consider just left and just right. So here up till this one, shear force at B, we have reached up to point B, but we have not crossed it. So when we cross this particular point B, we will be able to include this particular force acting upward, that is reaction at point B. Okay, so reaction at point B, so that was minus 6.5. So we have already calculated in the previous slide. Okay, this is minus 6.5. So shear force at point B, just right of the point B, is nothing but it is acting upward direction. So as per sign convention, left side of the plane in the upward direction is what? It is positive. So positive 6.5 kilonewtons. So like this we got the variation of shear forces from here to here. So friends, like this we got the variation of shear forces from this end to this end, from this end to this end of the beam. So all this variation I have shown here. The variation of shear forces for this uniformly distributed load is shown in this particular table. For point A is shown over here. So we can plot the graph of this as a shear force diagram. Okay, so we'll see that in the next part. So now we'll go for the third step, that is calculation of bending moments at various points. Since this is a cantilever beam, we will start moving from this corner of the beam. Okay, so we'll be starting from here. In the bending moment, this is basically a force given. So we need not to take just before the force and just after the force, because this will not change the value of bending moment. Okay, so cantilever beam, we start from the free end. So that makes calculation very simple. So we start from free end A. So we can directly find out the bending moment at point A. Okay. Then we take a section at point C. So we find bending moment at point C. From C to B, there is a uniformly distributed load. So we will have to continuously take various points from C to B in order to get the variation of bending moments. And then we can find out bending moment at point B, like that. Here we don't have to take bending moment just before the force and after the force, because force is not going to affect the bending moment. Bending moment will be only affected due to the application of moment of forces. Okay, so let's begin and do it. So I'll be considering a plane at point A. So we'll consider a plane at point A, for example, here, and we'll find out the bending moment at point A. So there is a sign convention for bending moment we should write down. So if your beam is bending in this way, it is called as sagging. If your beam is bending like this, it is called as sagging, friends. So this is called as positive bending moment. And if your beam is bending like this is called as hogging. This is called as negative bending moment. Okay, so positive and negative bending moments. So this is called as positive bending moment and this is called as negative bending moment. So we will see how the beam is going to bend as we proceed from point A to point B, like this. So when you are at point A, if you see that there is no force acting in the left hand side of this particular point, so there is no question of any kind of bending moment. Due to 2 kilonewton, because it is acting at the same point, it will not create any kind of bending at this particular point, because the distance between the line of application of the force and the point A is 0. So it will not create any bending moment. So I'll straight away write down bending moment at point A will be 0. Now we will try to take bending moment at point C. So our plane is going to be at this particular point C, and we will try to see at this particular point what bending moment is caused by the forces acting at the left side of this particular plane, because we are moving from here to here. We are considering the forces which are coming into the range of this particular plane. Okay, so now we have just one force, that is 2 kilonewton acting at distance 0.5. So due to application of this 2 kilonewton, your beam may bend like this, friends. Your beam may bend like this, right? So this is a kind of, so if you look at the shape of this, if you continue this shape, it may be something like this, friends. So it is kind of hogging kind of shape is created. So this is negative bending moment caused by 2 kilonewton. So this I will be writing as, so I can say that it is 2 kilonewton into this distance. This shape is hogging, friends. So it is minus 2. So it is minus 2 kilonewton into distance is 0.5 meters. So this value will be minus 1 kilonewton meter. Now we have got the bending moment at point C. So we have to find the variation of bending moment from point C to point D, and there is a uniformly distributed load acting from point C to point D. So your bending moment is going to vary continuously from point C to point B. Okay, so in order to find bending moment from point C to point B, what we will do, we will take number of points in between. So first we will consider an arbitrary plane. Let's say I am considering a section plane somewhere here, friends. Okay, and it is at distance, let's say, so this plane is at distance from point C, it is a distance, let's say x meters, like this. So as we will be moving towards B, this value of this location of this plane, that is, I am calling this plane as capital X, capital X. So this plane will be moving towards right. Okay, so this plane can be starting from point C and it is going towards right up to point B. So as it is moving, the value x also is going to change. Now what I'll do is, I'll take few points between point C and D. So let me take one point here, let me call this point as D, and let me take one more point here and let me call this point as E. So the distance between point C and D will be, this distance will be 0.5 meters. Similarly, this distance will also be 0.5 meters, and the distance between E and D is also 0.5 meters. I have taken 0.5 meters for simplicity because it will be easy for me to calculate. So now I got 1, 2, 3, 4 points over the entire length on which uniformly distributed load is acting, so that I can easily find out the variation of bending moment from C to B. Now let me find out the expression for bending moment corresponding to this particular location or this particular plane. So bending moment at section XX. So bending moment at section XX means at distance x from point C. So I'll call it as bending moment x. So when your plane is here, so first bending moment will be caused by this particular load, that is 2 kilonewton, and this will try to bend the beam in this fashion, okay, which is a kind of hogging, you can see here. So this shape looks like hogging. So this will be negative bending moment due to 2 kilonewton, and distance from here to here will be 0.5 plus x. So the bending moment due to this particular force will be minus 2 into the distance is 0.5 plus x. Now this much uniformly distributed load is there. This will also cause bending moment at this particular section. So this will also try to bend your beam in this fashion, which is hogging, friends. But here we have got the uniformly distributed load. So to calculate the bending moment due to force, we'll convert this uniformly distributed load into point load, and for that we will multiply this much portion, this much length with the load intensity. So it will be acting somewhere here at the midpoint, at the center. So this load will be, friends, 3 into overall span is x, so 3 into x, intensity into length, and it will be acting at the midpoint of this. This distance is going to be, friends, x. So from here to here distance is going to be, friends, this distance will be x by 2. Okay, so now we'll find out the bending moment at this section due to this force, that is 3x. It is going to bend in this way, so it is hogging. So minus intensity is 3 into x, and distance is the center or the midpoint of the length, that is x by 2, 3x into x by 2. So this is the expression we got. Let me simplify this expression, friends. Bending moment at x will be minus 2, 0.5 plus x, minus 3 by 2 x square. Okay, so we got the expression for bending moment at section XX. So now we will try to calculate the bending moment at point C, point D, and point B. Okay, please remember, at point B there is a moment MB is acting over here. So this moment will be only considered when we cross the point B. Okay, so up to the point B it will not be applicable. As we cross it, that is, so just before point B I will not consider this bending moment. Okay, I will only consider this bending moment when I will cross this particular point. So in this expression I will be just before point B. Okay, and after that I will consider this also once we go just after the point B. So first of all I will start calculating bending moment at C, D, E, B, and after that I will consider this bending moment and I will call it as bending moment after point B. This is very important. Wherever moments are acting, there we have to consider before and after. Okay, so before, it means we will not consider the moment acting at the same point, and after, when we go, then only we will consider that particular moment acting at that point. This will be more clear once I explain you further. Okay, so let's continue, friends. So I have drawn a table here. In this table I'll be showing various locations. So here there will be points. So we have the points here. I'm writing points, and here I am writing the bending moment at corresponding points. So first of all I am going to take point C. This is point C, friends, and then I'll take point D, then point E, and B. When I say B, just before, it is just before point B, because if I go just after point B, then this moment will come into the picture. So I'm just going before, just before point B. Okay, just before point B. So let's see what will happen when you are at point C. So at point C, your x will be, when you put this plane at point C, x will be 0. So I'm going to put x over here 0. This x will be 0. So this 3 by 2 will be cancelled out. So you'll have minus 2 into 0.5, and this value is nothing but minus 1 kilonewton meter. Hope it is understood. Already we have calculated that value, that is minus 1 kilonewton meter. Now we'll find out bending moment at point D. So when I find bending moment at point D, this plane is going to be here. So distance will be 0.5 meters. So distance is 0.5 meters. So we'll put that 0.5 meters here. So 0.5 plus 0.5 is going to be 1. So minus 2 into 1. And this will be, again, value of x is going to be 0.5. So 3 pi 2 into 0.5 square. So if you simplify this, you will get the value of bending moment at point D will be minus 2.735. Again the same unit, kilonewton meter. So this is what we got, the bending moment at point D. Now we'll find bending moment at point D. So we'll put this plane here. The distance is going to be, this distance is going to be 1 meter. So 0.5 plus 1 is going to be 1.5. So minus 2 into 1.5 minus 3 by 2 into x is again 1 here, friends. Your plane is here, your x is 1. So into 1 square. This value is going to be minus 4.5 kilonewton meter. Now just before point B we are considering, so bending moment, I am writing E only, but it is just before point D, friends. Just before point D, the distance is going to be 1.5 meter. So 1.5 I will put here. So 1.5 into 0.5, 1.5 plus 0.5 is going to be 2. So minus 2 into 2, and here minus 3 by 2 into x is 1.5. So 1.5 square. If you simplify this, the value will be minus 11.375. Minus 11.375 kilonewton meter. So we got the variation of bending moments from point C to B just before B. Now we'll also find out the bending moment just after B. So I'll write down here, friends. So bending moment just after B. So when I say just after B, it means whatever I got here, in that when I cross it, when I cross this particular plane just after it, this much bending moment would come into the picture. Okay. So this 11.375, in this value the bending moment, so this moment will be acted. So because of this moment, what will happen when you rotate the beam, when you put rotation like this, your beam is going to rotate in this way, like this. In this form, your beam is going to bend. Okay. So this is basically a sagging kind of bending moment. Okay. Due to application of this moment, the beam is going to bend like this, friends. So the sagging, it means whatever value you got, in that you have to add this particular moment. So we have already calculated the moment reaction here. So the moment reaction, what we got is, if you remember, the moment reaction we got over here was 11.375 kilonewton meter. Okay. So here this reaction we got. So it's very simple. It's very trivial that whatever bending moment we got here, just we cross, then this value will be added into it. Okay. So just we have minus 11.375 plus this value would come into picture, that is 11.375, and that is going to be 0 kilonewton meter. Once we cross it, then this value would come. Okay. So having understood this much concept, we got all the variation of bending moments from A to D. Please remember, whenever moment will act, there while calculating bending moments, you have to consider before that, before application of bending moment and after application of bending moment. So first we will find the bending moment without considering the moment acting at that point, and later on we will consider that, and both the variation we will represent. That is very important. We will see some more examples where I will put this kind of bending moment somewhere in between, so that your doubt will be more clear. For time being, kindly remember, before B we will not consider this moment, after B only we will consider this moment. Before means just before, and after means just after. Okay. So now we got the variation of the bending moments also, friends. Okay. So the next step would be to plot the variation of shear forces and bending moments, and that plotting is called as shear force diagram and bending moment diagram. So let's do that also. So friends, here I have written the complete information about shear force and bending moment. So we got shear force at A, just left 0 and just write minus 2 kilonewton. This already we have calculated. And then shear force variation from point C, D, E, and then at point B. Okay. So all that shear force variation I have shown here. Similarly, bending moment variation I have shown. So bending moment at point A is 0 we got, and C also we got, and further C, D, E, before B and after B also I have written over here. So with the help of this information, we can now plot the shear force and bending moment diagram. I have plotted horizontal lines like this. This line represents shear force, so this is called a shear force diagram, SFD, and this axis is going to represent bending moment, so this I am going to call as bending moment diagram, that is BMD. So we have also considered two more points in between, that is E and F, that also I will show. So this grid line represents point D, and this grid line represents point E, and the distance is 0.5, 0.5, 0.5 meters each. Now I am going to first draw the shear force diagram with the help of these information. So shear force just left of point A is 0, so this is going to be 0, friends. So this is 0 kilonewton, I am writing 0 kilonewton just left, and just right is 2 kilonewton, you can see, but negative it is. You can see minus 2 kilonewton, so that I also write. So it is going to be somewhere here, and this value is minus 2 kilonewton. Okay, so we got from 0 to minus 2 when you cross from here to here. At point C, if you can see in this table, at point C is also it is minus 2 kilonewton, so the same value would come at the same level. I'll be getting here somewhere here. This value is also minus 2 kilonewton. So I'll write down here minus 2 kilonewton. Okay, so it remains horizontal. Okay, same value you're going to get from here to here. Fine. Now if you see the variation due to uniformly distributed load at point D, which is at 0.5 meter, we got is minus 3.5. So here we are getting, let's say, minus 3.5 value. Okay, at point D. At point E we are getting minus 5 kilonewton. So here we are getting, let's say, minus 5 kilonewton. Minus 5 kilonewton. And at point B, the last point here, okay. So at point B we are getting minus 6 kilonewton, right? So we get somewhere here, and this value is going to be, so here we are getting minus 6 kilonewton, minus 6 kilonewton. So again here, because there is a point load acting and this reaction is 6 kilonewton, we have calculated already this reaction. So when we just cross it, so shear force just after point B, okay, will be minus 6. This already we have calculated. So minus 6 plus 6 is going to be 0. So that is 0 kilonewton just after. Once we cross this particular point, so this force would come into the picture. So here we got this already, we have done it. Okay, just go back and see the video. There already I have calculated. So at B we have calculated before and after. So it is, once you cross it, it becomes 0. Okay, because already here just before it is minus 6 and after it is minus 6 plus 6, that is going to be 0. Okay, so you get 0 value here. So you get 0 over here. So 0 kilonewton. So this was the variation, friends. So we can plot this variation now. So it goes from 0 to minus 2, then it remains flat like this, and then it increases something like this, friends. So linear variation up to here. It's a linear variation, please remember, and then from here it goes to 0, something like that. Okay, so this is how we got the variation of shear forces, and this is a linear variation. So we get a linear variation like this. This is basically the shear force diagram we got, friends. So shear force varies from 0 to minus 2, remains minus 2 up to here, then it varies linearly up to minus 6, then becomes 0. So this is, friends, shear force diagram, and it's a negative here, you can see negative shear force diagram. Okay, because it is coming below the horizontal axis. So this same way we'll be plotting bending moment diagram. So let's see what are the values of bending moment. So you can see from here the bending moment at point A, this particular point is going to be 0. Okay, so there is 0 bending moment here, 0 kilonewton meters. Now then we got the bending moment at point C, which is minus 1. So let me write it down here somewhere here. Let's say, friends, minus 1 kilonewton meter. Now next point we got is at point D. So at point D we are getting minus 2.735. So let's say somewhere here, friends, minus 2.735 kilonewton meters. So point D we got. Point E we are getting minus 4.5, somewhere here, let's say minus 4.5 kilonewton meter. And at point E, at point B, just before it is minus 11.375. So somewhere here I am going to show somewhere here minus 11.375 kilonewton meter, and just after if you go it becomes 0, so 0 kilonewton meter like this. So but this variation, if you look at here, this variation, friends, this variation is basically, its expression is in terms of x square. So this is a square variation, second degree curve variation. So we'll plot that. So from here it is second degree curve. So this curve is second degree curve, friends, something like this. From here to here, it is going to be straight line, because it was 0 here and then it became 1. It's a straight line variation. Okay, inclined line is going to come into here. So this is, kindly remember, this is going to be second degree curve and this is going to be further straight line. So friend, this is the diagram which represents the variation of bending moments. Please remember, point A to point C, the bending moment is going to be straight line, so I have written linear over here. Point C to point B, this is second degree curve. Okay, there is a curve over here, and since the bending moment is coming downward, so this all bending moments are negative. So negative bending moment we are having, friends. Shear force is also negative and bending moment is also negative. So this way we can plot the variation of shear forces and bending moments for this kind of beam, which is a cantilever beam. Okay, thank you very much.